Otherwise, we cannot the time for some. Right. So hello and welcome everybody to our last colloquium of this academic term. Today we have the pleasure of having Professor Mark Alford giving our colloquium. As usual, let me just give some brief CV. Mark did his undergraduate in Oxford, then his PhD in Harvard. And afterward, he had some postdoctoral positions in Santa Barbara, Cornell, MIT, and Princeton. And then since 2003, he's a professor at Washington University in St. Louis. Mark is one of the world experts on high-density QCD. He started more as a particle physicist and now has been transitioning more into the nuclear astrophysicist. But he has done very important work in many areas related to the high-density part of QCD, from theory to computational methods and also applications in terms of nuclear stars. He is one of the proponents and experts on the color superconducting phase. He has very important works on the consequences of quark matter in neutron stars. And lately, he's been very active in trying to understand transport and excitations and the effect of electroweak interactions in neutron stars. And this is part of the topics that he's going to talk about today. He's going to talk to us about neutron stars mergers or material science. And so I'm sure that you prefer to listen to him, not to me. I give the floor to Mark. Thank you, Mark, for accepting our invitation.
Thank you very much. You can hear me. I can hear myself, so I know you can hear me. So yes, thank you. It's a great pleasure to be here. It's always a great pleasure to visit Barcelona. I arrived on Saturday and discovered that every weekend you have amazing fireworks and explosions, and it was just fantastic. So I look forward to seeing that whenever I come back. So yeah. Oh, interesting. Why don't we... There we go. I killed it. So today I'm going to talk about this topic. This slide here is meant to show you where I'm from. It's Washington University in St. Louis. It is not Washington, D.C. It is not University of Washington in Seattle. Those are at the other ends. This is in the middle. We are a famous city because we have half a McDonald's. This arch, which we're very proud of, and we have beautiful buildings, and life is great, but not as much fun as here. Okay, so yes, what am I going to talk about? So I'm going to talk about neutron star mergers. I'm going to talk about them from a sort of more microscopic physics perspective, from the perspective of someone who's interested in particles, who's interested in the behavior of matter. So the relevant thing is that to us in that community, neutron star mergers are a wonderful experiment that nature does for us. And you've probably heard talks about neutron stars and neutron star mergers. And most of the time, what you'll hear about is the equation of state. That's the thing people mostly talk about. And the equation of state is very important. But I'm going to talk about something that is not an equilibrium situation. I'm going to talk about the out of equilibrium properties of the material, the matter, the nuclear matter that is in neutron stars and that is in mergers. So examples of what you mean by out of equilibrium phenomena would be things like, the main one I'll talk about is flavor equilibration. That's equilibrating the proton fraction in nuclear matter. And that is related to a material property called bulk viscosity. You could also have thermal equilibration, different regions at different temperatures, and they have to equalize out. That happens through thermal conduction, so that's thermal conductivity. You could also have shear flow equilibration. One part is moving faster than another part, and so there's a shear difference in their velocities, and you can get shear viscosity that way. And the main reason for looking at these properties beyond the equation of state is that these are better than the equation of state if you want to probe the phase structure, the different phases. So, for example, a lot of this relates to terrestrial, ordinary, everyday condensed matter physics. This is why I called it material science. We're using the same concepts. So if I gave you a piece of metal and I asked you, is it a superconductor? Is it in the superconducting phase or the normal phase? You would not measure its equation of state. Right? You would not compress it and see how difficult it was to compress. What would you do? You'd attach leads to it and you'd put a voltage across it. You'd push it out of equilibrium by putting this voltage across it, and you'd measure the response. So very often the equation of state is pretty similar in different phases. Not always, but very often. So a better discriminator of phases is these out of equilibrium phenomena that relate to these. Often they're called transport phenomena. So the one I'm going to talk about is flavor equilibration. So let me just sort of give the big picture that we're going to explore. So the question is, flavor equilibration, is it important in neutron star mergers? And for that, we'll be looking at various things. We'll look at the relaxation time for the proton fraction. That's how long does it take for the proton fraction to go back to its equilibrium value if it's pushed away for some reason. We'll look at this thing called critical equilibration, which is when you can't ignore that sort of relaxation. Okay, you have to include it. You can't just ignore it. And we'll look at the physical manifestations of this relaxation to equilibrium. And that is, as I said, things like bulk viscosity and damping or attenuation of sound. So these are all things that happen on Earth here. These are all things that you've heard of, right? That you're used to the idea that in air, sound is attenuated, and you're used to the idea that materials have viscosity. And we're pursuing the same project. It's just instead of lumps of metal or lumps of silicon, we're talking about an enormous lump of mostly neutrons, you know, far away. Okay, so I talked about phases, and so I always have to show this slide. This slide is part of every talk on this topic. So you have a phase diagram. So here we have chemical potential, which is basically driving density to higher values. And here we have temperature, which is driving entropy to higher values. And so you can heat it up at the top end, or you can squeeze it over to the right-hand end. And this is matter. So you have a vacuum down here. You have hadronic matter made of protons and neutrons. If you heat it up enough, you have the quark-gluon plasma. This is done in heavy ion collisions. And in neutron stars, you have nuclear matter, just neutrons basically all packed together. So that's very dense nuclear matter. And neutron star mergers occupy this area where you take neutron stars, you smash them together, and you get higher density, and they heat up. Okay, so this is what happens when you smash big chunks of nuclear matter together. You get mergers. If you smash little tiny droplets of nuclear matter, nuclei together, then you're doing heavy ion collisions, and you get mostly heat. So, okay, by the way, where are you on my phase diagram? Can you find yourself? This is like, do you have Where is Waldo or some similar thing in Catalonia? Yeah, where are we on this phase? Any suggestions? Can you see yourself? Sorry, at the origin. The origin's a good guess. You're not that hot and you're not that dense. But the origin here is the vacuum, right? That's empty space. There's nothing there. So I'm not going to, say that that's you. Where are we? Where are we? Where we are is here. Let me actually point to it. We're here because we are a mixed phase. What are you? You are a mist of little droplets of nuclear matter, nuclei, surrounded by electrons. That's chemistry. Okay, so you are this mixed phase, little droplets of nuclear matter with vacuum or electrons in between. Okay, so you are a mixed phase of partly vacuum and partly nuclear matter. So you are here on this diagram. Okay, so this is the phase diagram in the terms of how nature probes it. Here is our speculation. We have all these ideas about, this is all in red here, all these ideas that there's a critical line here, a chiral and deconfining phase transition ending at a critical point. There's a color flavor locked phase of quark matter somewhere up at very high densities. Who knows what there is in here? And part of what's nice about neutron star mergers is that potentially they may be exploring some of this interesting region of the phase diagram where there may be interesting phases that we don't know about yet. So yeah, that's basically the point of that. Okay. So yeah, which parts of the phase diagram do you explore in a neutron star merger? So I went to the people in Frankfurt, the Razzola group, and they made for me a very nice map here. So here is density along the bottom in units of nuclear density. So nuclear density, twice nuclear, 3 times, 4 times. And up the side here is temperature in mega electron volts, 10, 20, 30, 40, 50 mega electron volts. And they did one of their simulations. And when they smashed the 2 stars together, they took every little fluid element and they plotted its temperature and density on here. So you can see which regions of temperature and density are explored, created in a neutron star merger. And they did it, they got it twice here, 2 milliseconds after the stars touch and 10 milliseconds after the stars touch. And the point of this slide is just that you're exploring quite a good range of temperatures and densities. You can see after the stars touch, you've got maybe 1, 2, 3 times saturation density and temperatures up to maybe 60 or 70 MeV. The details will depend on the simulation, the equation of state and stuff like that, but the overall idea is that. And after a while, it settles down. The middle is not that hot. This is the middle here. The color tells you how many kilometers from the middle. So the middle is dense, but not that hot. The outside is not that dense and not that hot. And there's this sort of middle region that's fairly dense and fairly hot. But the point of this slide is to show there's a lot of variation. It's not all the same temperature. It's not all the same density. And as time goes by, the density and the temperature at a given place change. So this sort of spatial or temporal variation is going to lead to things going out of equilibrium, right? In equilibrium, everything would be the same everywhere. But this is showing you that a neutron star merger drives the material out of equilibrium. You've got variation in temperature, so you'd have thermal conductivity trying to restore the same temperature everywhere, fluid flow velocity with shear viscosity, and you've got variations in density. The density is changing. So as we'll see, that changes the flavor content and can give you bulk viscosity. We'll explain that. Okay, I'm just saying it for now. So let's think about, okay, we're going to focus on density variation. Okay, so let's imagine that a neutron star merger happens, and I'm going to make you into one of the fluid elements. So you are some little piece of nuclear matter. You're in a neutron star. You thought everything was fine. You didn't know there was another neutron star nearby going round and round and round. And suddenly they smash into each other and your life changes dramatically, right? Instead of being a little piece of nuclear matter with the same density and the same temperature sitting in equilibrium, suddenly chaos erupts. And so what the people who do these simulations can do is they can track little fluid elements, okay? And they can find what would you as a fluid element experience after the merger? What would happen to your density in particular? So they have a plot here where they took various different fluid elements, they call them tracers, okay? And for the first 20, 25 milliseconds after the merger, they track little fluid elements and plot how does their density vary in time. So here is a bunch of these tracers. And what do you see? They start off, they were selected, I guess, by Razzola and his students around twice nuclear density. This is density here, this is time here. So they start off around twice nuclear density, but for about the first 5 milliseconds after the merger, look what's happening to their density. Absolutely crazy, right? They get squeezed down to much higher density, rarefied to lower density, squeezed to higher density, unsqueezed to lower density, squeezed to higher density. They're feeling dramatic density oscillations. These are high amplitude, right? Look at this. I haven't shifted the origin, you know, this goes down to 0. So these are maybe up to 50% density oscillations. They have a period, if you look, this is milliseconds here, 5, 10. So the period is in the sort of 1 millisecond range. So these are kilohertz, right? Kilohertz, basically violent sound waves, density oscillations. And then after about 5, 10 milliseconds, things settle down a bit, and they're still oscillating, but a slightly more moderate amplitude. So what we learn from this is that indeed there are very strong density oscillations, particularly in the first few milliseconds after the merger. Fluid elements are going to experience violent changes in their density with a period or a frequency that's in the kilohertz range. Does this make sense to everybody? Are we excited to see the next stage of the story? What's going to happen to our poor little fluid elements? Okay. So the questions we're going to ask is, how does this relate to the thing I was talking about, which is equilibration? In this case, flavor equilibration. So do these density oscillations drive the system, where by the system I mean little fluid elements? Does it drive them out of flavor equilibrium? And does that, in turn, back react on the oscillations in some way? So let's talk about the fluid. Okay, I haven't, up to now, I just talked about it as stuff and neutrons and everything. So let's be a bit more definite. What are we dealing with? So here's some generic fluid element. What's it got in it? When we're dealing with neutron stars, we're talking about a nuclear matter fluid. So it's mostly neutrons, these blue dots here. There's a small fraction of protons. We'll see exactly what fraction it is going to be the main interesting thing that we follow. There's going to be enough electrons to keep it electrically neutral, because if it was charged, it would just attract charge into it to neutralize itself. And then there are neutrinos, and neutrinos are sort of the complicated factor here, because neutrinos don't always thermally equilibrate, because they only do weak interactions. So they're kind of a problem, and we're going to try and sort of mostly treat them in a simplified way. Eventually, we hope to be able to do a better job, but for now, we have to sort of make some assumptions about neutrinos. So if this is your generic fluid element with protons, neutrons, electrons, and some neutrinos in it, then it's described by 3 or 4 parameters. So if you want to tell me what's the state of a fluid element, what do I need to know? I need to know the baryon density, neutrons plus protons, total baryon density, how many of them per cubic femtometer. I need to know the temperature. I need to know the proton fraction, what fraction of the baryons are protons, and if neutrinos are equilibrated and trapped, then I'd like to know the lepton fraction, but we're not going to talk about that situation so much. So most of the time, we're really going to think about this 3-parameter thing. It's got a density, baryon density, it's got a temperature, and it's got some proton fraction. What fraction of those baryons are protons? Does this make sense to everybody? You all okay with that? All right. So the equation of state, the thing that you mostly hear about in neutron star talks, is just a function of these things. What's the pressure for a fluid element with a given baryon density, temperature, and proton fraction, and maybe lepton fraction? What's the pressure? What's the energy density? What's the entropy density? All these things. That's the equation of state. That's the equilibrium that it would settle down to if you gave it an infinitely long time. This fluid element would settle down. But we're interested, remember, in that crazy momentary chaos after the merger where things are not settled down. So that's what we want to look at. So let's think about these density oscillations. So each fluid element has an equilibrium proton fraction, which is determined by weak interactions. So if you set the density and the temperature, then weak interactions will happen. They can turn neutrons into protons, protons into neutrons, and they'll operate until it settles down to its happy place, right? The proton fraction it likes to have. And this is determined by properties of the strong interaction and electrical neutrality. And okay, we'll take it as a given thing. There's an equilibrium proton fraction. So for a density and a temperature, there's some proton fraction it wants to settle down to. So here's what it looks like for some particular equation of state. It's called IUF. It's a model. Obviously, we can't do the strong interaction exactly. So this is a model of nuclear matter. This is at t equals 0. let it equilibrate, and here's the proton fraction at different densities. So nuclear density is 1, twice nuclear, 3, 4, 5 times nuclear, and so on. And here's the proton fraction up the side. So you can see the typical proton fraction is in the sort of 5 to 10% range. Okay, not a huge amount, but not totally negligible. So if you're a fluid element at twice saturation density, and I let you settle down, you'll have about 8% protons, right? 8% of your baryons will be protons, 92% of them will be neutrons. So there you are, that's you. Now, imagine though, you're one of these little fluid elements that I was talking about before, that when the neutron stars hit, suddenly gets compressed by a factor of 50%, okay? So supposing we take you with your 8% proton fraction, and suddenly, in this merger, you get compressed to 3 times saturation density. Well, now, you want to have a different proton fraction. You want to have 10% protons. And that means that the weak interactions are going to start turning some of your protons into, some of your neutrons into protons to increase your proton fraction. Now, this is not necessarily an instantaneous thing, because weak interactions take time, right? How long does the neutron take to turn into a proton? If I just gave you a neutron right now, right, and you have to wait for it to turn into a proton, how long does that take? About 10 minutes, right? That's the lifetime of the neutron in vacuum. So here, it's a different time scale. It's some other time scale. That's really what we want to calculate. But it's, it's not instantaneous, is the point. So that means there's a good prospect that these density oscillations, where in a millisecond you go from twice to 3 times saturation density, that's going to drive the system out of its flavor equilibrium. And these words all mean the same thing. They're all talking about the proton fraction, right? So when I say flavor equilibration, I just mean getting the proton fraction back to its equilibrium value. Beta equilibration, it's just a word people use, same thing. Chemical equilibration, another word people use, means the same thing, get the proton fraction. And the isospin, since the difference between protons and neutrons is isospin, you can also call it isospin equilibration. So all these things just mean the same thing, relaxing the proton fraction back to its equilibrium value. Okay, so we're interested in the question of, when you get driven away from this line, what happens? Okay, if you get driven away from the equilibrium, what is going to happen? That's our question. So let's think about this. Let's make a little model. Okay, so we can model this. So let's say we imagine some fluid element that undergoes a density oscillation like this. It's got a baryon density that's a function of time. It's got some average baryon density. And then on top of that, we put some density oscillation, make it a nice cosine. We're just sort of modeling it to get an idea of what happens. It's got some angular frequency omega, so that's the frequency of the density oscillation, and it's got some amplitude delta n. So we're sitting here and we're squeezing it rhythmically, at some frequency and with some amplitude. Okay, so that's the fluid element. And then we also put in this relaxation of the proton fraction. So we say the proton fraction changes in time. Its time derivative is minus some rate times how far it is out of equilibrium. Okay, so this is just a very simple relaxation equation. If you let this go, it will reduce or increase the proton fraction until these two are equal, and then the proton fraction won't change anymore because this is 0, right? Basic relaxation equation. So, but because of this oscillation here, this equilibrium proton fraction is changing, right? There's a moving target for this relaxation equation because the baryon density is varying, so the equilibrium proton fraction is varying. We just saw that. So this relaxation equation is chasing a moving target. Okay, it's always trying to relax towards something, but the something keeps changing. So let's think about how that's going to work. Okay, so let's think about different cases, because we've got two rates here. We've got the frequency and the relaxation rate. So we can compare them. So let's imagine fast relaxation. Let's imagine those weak interactions are fast, and so this relaxation happens very quickly, okay? So here, this is a sort of cartoon of the thing I had before, where the proton fraction is a function of density, okay? So you imagine I've got some fluid element, I'm wiggling its density around, like this. Where in this diagram is the fluid element going to go if I'm wiggling the density as a function of time? What am I going to see when I solve this equation and plot it on this diagram? What's it going to do? Yeah, wave your fingers. Show me waving fingers. I want to see waving fingers. Go on, wave those fingers. Come on. fingers need to do something. They're bored. Your brain is doing okay, but your fingers are very bored. Okay, so yes, I'm seeing fingers going like this. Okay, fingers going like that. So it equilibrates very quickly. So when you compress it a little bit, it just instantly equilibrates. You compress it a bit more, it equilibrates again. So yes, if you solve this in the situation where equilibration is fast, it just always tracks equilibrium. It stays very close to equilibrium. You compress it, you uncompress it, you know, this thing goes back and forth, back and forth. It stays on the equilibrium line. So the proton fraction always stays in equilibrium, and that means you actually don't need to solve this relaxation equation. If I tell you the density, you can just tell me the proton fraction, right? It's in equilibrium all the time. You don't need to solve the equation at all. So yay, less work. Okay, let's look at another case. Let's look at the case of slow equilibration, right? So slow equilibration. Now what am I going to see? Get that finger. You thought it was over. It's not over. Okay, finger. Okay, some fingers are doing different things. Slow equilibration. Okay, slow equilibration. Yeah, I'm seeing some hesitant fingers. Some fingers doing the right thing. Some fingers wandering. Interesting. Okay, various different fingers. All right, we won't name any names. Okay, so what happens if it equilibrates very slowly? Then when I compress, suppose you start off here, you've got a proton fraction of whatever it is, 6%. Okay, I compress you. You're not relaxing. What happens to your proton fraction? Still 6%, right? So this is what it'll do. Okay, if the relaxation is very slow, the proton fraction doesn't care, right? You compress it, it's still 6%. Uncompress it, it's still 6%. Doesn't change. Okay, so it's just going back and forth. So again, actually, you don't need to solve the relaxation equation. The proton fraction is just determined by history, right? Whatever the proton fraction was at the beginning when we started, that's what it is forever. Okay, so that number, you know, the historical, the traditional proton fraction of this fluid element is just fixed and doesn't change. So again, we don't need to solve the relaxation equation. Okay, is it over? We don't need to do this? No solving of relaxation equations? Everything is fine? Is there anything else I need to do here? What do I need to do? Any other situation I should look at? I've done slow equilibration. I've done fast equilibration. What about if they're about the same? Okay. What happens if the relaxation rate is about the same as the frequency of the oscillations? Okay, so here's this. Now I want to see, this is the last time that your fingers will be called upon to serve the nation. Okay, so what is the proton fraction as a function of baryon density going to look like now? I see some, I see some fingers that are, yes, okay. Some people are recycling things they used before. Okay, okay. Well, okay, I'll just tell you the answer. There we go. Okay, so what happens is you compress and it starts trying to get towards equilibrium. As you increase the density, it starts trying to move towards equilibrium, but it can't quite keep up. And then you start uncompressing again, and it's still trying to equilibrate to, you know, it's still out of equilibrium. So it's still trying to move upwards, and then it crosses, and then, yeah, okay, so it's lagging, right? It's lagging. The response of the system is lagging behind the applied stimulus, in this case, the density oscillation. So you get this thing. Now, what's interesting about this is that if I tell you the baryon density, you cannot tell me the proton fraction, all right? You need to solve that relaxation equation, okay? It depends on history. If I tell you that the baryon density is 3, well, the proton fraction depends on, are we in the compressing stage or the uncompressing stage of this oscillation? So in order to do that, you need to track the history, and that means you need to, as well as having that density oscillation, you need to include the relaxation equation in the dynamics in order to find out what is the proton fraction of this fluid element at any given moment. So this critical equilibration thing, where the relaxation rate is about the same as the applied density oscillation frequency, this is a very interesting thing, and we're going to talk about it really basically for the rest of this colloquium. It's when you have maximum phase lag between the density and the proton fraction, when this ellipse is most ellipse-like and not flat like it was in the other cases. And it's also, it turns out, I may get to this by the end, I may not, we'll see. It's when you get the biggest bulk viscosity and the most damping of density oscillations. It's when this relaxation of the proton fraction actually leads to real effects, which is that it sucks energy out of that density oscillation and turns it into something else, maybe heat. And that's what bulk viscosity is. But so before we get too excited about that, we need to ask, this critical equilibration thing where interesting things happen, does it actually happen in mergers? Okay, do we get the situation that the density oscillations are of comparable frequency to the relaxation rate? So that's our next topic, is do we get this in mergers? Any question at this point? Nobody wants to ask a question? Okay. We all on board? All right. Okay, so here's our mission. So, yes, is there critical equilibration in mergers? Well, there's only two things in this equation. There's one on the left and one on the right. So all we have to do is evaluate both of them and see if they're about the same ever. So the frequency, that was easy. Remember, we asked the merger people, they tracked the little tracers, and they told us that they experienced density oscillations that are about 1 kilohertz. Fine. So what about the relaxation rate? Well, as we've mentioned before, this is determined by weak interactions, these things called ERCA processes, named after a suburb of Rio de Janeiro in Brazil. And neutrinos play an essential role in those. And that's where it gets annoying, because neutrinos are a difficult player, because they're sort of sometimes equilibrated and sort of sometimes not. So we're going to look at two separate cases of how the neutrinos are behaving, two extreme cases of how the neutrinos are behaving. And the reality is probably somewhere in between, but we'll have to deal with that later. So we can calculate that relaxation rate in these two limiting cases. The two limiting cases are neutrino transparent. The neutrinos have a long mean free path. When they're created, they just fly out like radiation and disappear off into space. The other extreme situation is neutrino trapped. The neutrinos are just like the electrons and the protons. They don't travel very far. They locally equilibrate, and they form their own fluid. So it's just like a neutrino fluid along with the electron, proton, and neutron fluids. So these two extreme cases we can deal with. The reality is kind of in between, and that's difficult. So what are these ERCA processes that bring the proton fraction back to its equilibrium value? Well, neutron decay, which we just mentioned, happens in vacuum. There are probably labs in this department who can do this. Neutron decays into a proton, an electron, and an antineutrino. Or electron capture, you see this in some nuclear decays where, you know, an innocent electron strays too close to the nucleus and gets eaten. Okay, so an innocent electron gets eaten by a proton, turns into a neutron and a neutrino. So these processes can turn neutrons into protons or protons into neutrons, and these are the processes that get the proton fraction to its equilibrium value. In neutrino trap matter, you have neutrinos on both sides. It's the same process forward and backward. So in these two extreme cases, you can do the calculation. So I'm not going to do the calculation before your eyes. I'm going to show you the result. You will be happy to hear. So I'm just going to show you the result, and we're mostly going to focus on the neutrino transparent case, but I'll show you both to start with. So we just do the calculation. We calculate the relaxation rate, and we see, is the relaxation rate ever equal to the 1 kilohertz typical density oscillation frequency? And the relaxation rate itself depends on the density and temperature of the fluid element. So we could ask, at what density and temperatures, if any, is the relaxation rate comparable to this kilohertz timescale of the oscillations? Does that make sense? Any question about that? Have a big reveal here. Okay. So here's the calculation. So we do this in this, we show the results in this plane that we've used quite a few times now. Density along the bottom, 1, 2, 3, 4 times nuclear density. Temperature up the side, 1, 2, 3, 4, 5 MeV. And these contours show you that relaxation time, this gamma thing. In fact, it's 1 over it. So I'm showing the relaxation time, not the relaxation rate. So instead of being in kilohertz, it's in milliseconds. But those are just two sides of the same coin. So here you are in neutrino transparent matter as a function of density and temperature. What's the relaxation time? And if it's a millisecond or so, then it's close to critical equilibration. So what we see here is at low temperatures, it's 100 milliseconds, it's slow. But then as you turn the temperature up, it doesn't depend on density so much. These contours are pretty horizontal. Mostly depends on temperature. You turn the temperature up, the relaxation rate gets faster. And so it starts off being like a second or a tenth of a second at these 1 MeV type temperatures. But then when you get to 3, 4, 5 MeV type temperatures, it gets into the interesting range. That's this gray part here, is the range where it's, you know, of the same order as the 1 kilohertz frequency of the density oscillations that happen in mergers. And then it gets even faster. You cook it up to 8, 10 MeV temperatures. It's going faster, like a hundredth of a millisecond. So it's mostly determined by the temperature. And indeed, as you heat the fluid element up, its relaxation rate scans through 1 kilohertz, right? It's slower than a kilohertz at low temperatures, faster at higher temperatures, but there is a range of temperatures in the sort of single-digit MeV range where, indeed, you have this interesting critical equilibration. In neutrino-trapped matter, it's always too fast or very fast. So even at low temperatures like this, it's typically like a tenth of a millisecond, and then it's even a hundredth or, you know, a thousandth or a millionth of a millisecond, okay? So neutrino-trapped matter equilibrates very quickly. So that's going to be maybe in the category where it sits on the equilibrium line the whole time. But neutrino-transparent matter, depending, it could be equilibrating very slowly down at the bottom here, just going horizontally, remember? It could be equilibrating quickly and staying on the equilibrium line, but at the right temperature range, it could be doing what my microphone is making noise. Okay. It could be doing this thing. I have an idea. Let's see if that helps. So, okay. So what do we learn is relaxation goes faster at higher temperatures. It doesn't care that much about the density. These contours are pretty horizontal and is very fast in neutrino-trapped, but could get critical equilibration in neutrino-transparent. This thick contour here shows where you get the exact matching, that the relaxation time is 1 millisecond over 2 pi. So there you are, around 5 MeV. So okay, so there is the prospect, if there's neutrino-transparent matter at 5 MeV or 3 MeV in neutron stars, that you can get critical relaxation. All right, next question is, for those of you who are skeptical, does it matter what the equation of state is? So I replicated this neutrino-transparent thing for 2 different equations of state, just to show you it doesn't make that much difference. The contours look about the same. Okay, there's some uncertainty in the equation of state, so one has to worry about this, but it doesn't make that much difference. Okay, and this is the same things again. So that we conclude that critical equilibration is occurring at these sort of 5 MeV-ish temperatures in neutrino-transparent matter. All right, so let's have some conclusions so far. Okay, as you've survived long enough, you deserve some conclusions. I have more to say afterwards. These are not final conclusions. These are like midterms. Do you have midterm exams? Yeah, okay, this is like that. So in neutrino-trapped matter, the proton fraction relaxes very quickly. So only if you were doing merger simulations with super short time steps, like a microsecond, maybe then you'd want to track the relaxation of the flavor that would be happening in a microsecond. Neutrino-transparent matter, now it's part of the dynamics. Proton fraction equilibration is happening on the same time scale as the oscillation. It's part of the dynamics. You need to include it in some way. Now, in reality, of course, neutrinos have some non-thermal distribution of neutrinos. It's something in between these two. You know, I'm not going to try and deal with that. But okay, let's jump to the next question. So what's the next question? If we've got this critical relaxation thing going on, critical equilibration thing, where the relaxation time is comparable to the oscillation period, are there physical consequences of that? What does that actually do? So let's get onto that thing now. How am I doing with time, by the way? Give me a quick time check. 15 minutes, okay, all right. Okay, so yes, what would be the physical consequences? So for that, we need to think a little bit about, I know what, yeah, I'll show you the results first and then we'll think about it. So here's a result. You calculate the bulk viscosity, which involves the response of the system to compression, and you get these contours for the bulk viscosity. So it's in the same density temperature plane. It's the log of the bulk viscosity in this case in these wonderful astrophysical units. We love astrophysicists because they choose units that are appropriate to the gigantic size and weight of the objects they study, stars and galaxies. So let's work in grams. Okay. and centimeters. Okay, fantastic. So, okay, here's the bulk viscosity, and here are these contours. The bulk viscosity is big here, 10 to the 29 of these units, and then as you go outwards, it gets smaller. Okay, non-monotonic temperature dependence, it's small, and then it gets big, and then it gets small again. Not very sensitive to density. Does this sound familiar? Okay, all the exciting stuff happening at about 5 MeV, that's where the biggest bulk viscosity is, and the density doesn't matter that much. Well, that does sound kind of familiar. Let me go backwards and say, that sounds a lot like this plot, where all the exciting stuff happened at 5 MeV, that's where the critical equilibration was, and the density didn't matter that much. So indeed, they're connected. Bulk viscosity is connected to critical equilibration. So let me show you why. So let's think about what bulk viscosity is. So bulk viscosity is what you get when you've got some material, and in our case, it's neutrons and it's a proton fraction, but it could be something else. It could be something, you know, ordinary and terrestrial with some degrees of freedom that are slow to equilibrate in a lump of material. But some degree of freedom takes time to equilibrate. And the result is that when you impose a density oscillation, the density and hence the volume of a fluid element go out of phase with the pressure. So here's what you imagine. You imagine you are squeezing this fluid element. So your arm is doing a piston thing, right? Here's a cylinder of fluid, and you compress and you uncompress. So you're doing the cos omega t, right? That's you. That's your muscle is doing that cos omega t compression thing. And how much work does it take? Well, you compress and you have to do work, right? It's like a spring, right? But then you uncompress and it does work on you, right? And if it's a perfect spring, then those even out. So you can measure how perfect is it? How much energy do you end up losing at the end of the day when you compress and you uncompress? So that's just this PdV work. You know, work is force times distance. It's just PdV work on the way in, done by you, PdV work on the way out, done by it. And we just integrate that over one cycle, and we see what's the net amount of work done by you. And you can convert this, and you can just put in a dt, and so it becomes the integral of the pressure, the rate of change of volume, integrated over one cycle. So this is going to tell you how much work you did to compress and uncompress. So with a perfect spring, the answer is no work is done. Here's the pressure and the volume. You increase the pressure and the volume goes down. Right, you increase the pressure, the volume goes down. You decrease the pressure, the volume goes up. And it always goes back and forth along the same line here, right? It's a perfect spring. So at every stage, when you're squeezing it, the amount it resists you at a given point on the way in is the same as the amount it pushes you at that point on the way out. So the whole thing is symmetric, right? The work you do on it and the work it does on you equalize, and there's no dissipation. And in that case, the pressure is perfectly, oops, let's go back. The pressure is this red thing here, and the volume is 180 degrees out of phase with the pressure. You squeeze it and it gets smaller. You unsqueeze it, it gets bigger. And dV dt here, a d by dt is a 90-degree phase shift. So dV dt is 90 degrees out of phase with the volume. And since the volume was 180 degrees out of phase with the pressure, dV dt is 90 degrees out of phase with the pressure. And if you do the integral of two things that are 90 degrees out of phase with each other, you get 0. So this is the sort of complicated way of thinking about it. This is the simple way of thinking about it. You can think about it however you like. Now let's think about what happens if this material is not always in equilibrium, because what's happening here is it's always in equilibrium, right? You squeeze it, it always instantly goes to the equilibrium state at its new volume. But suppose that doesn't happen. Remember that, you know, your finger remembers, right? That you had this circle where the state of the system during compression is different from the state of the system during decompression, right? Remember, the proton fraction on the way in was different from the proton fraction on the way out, because it's always trying to catch up and never quite succeeding. So now you get a similar kind of ellipse in the pressure volume plane. When you're compressing it, you increase the pressure and decrease the volume. But when you decompress it again, it doesn't follow the same track back again because it has some memory. Its proton fraction is different because it's remembering that it was recently in a compressed state. And when you're uncompressing it, when you're compressing it, it's remembering it was recently uncompressed. So it's got this memory because something inside it is reacting on the same time scale as the oscillation you're imposing. So now the pressure and the volume are not 180 degrees out of phase, and now dv dt is not 90 degrees out of phase with the pressure, so this integral is not zero. Or in other words, there's an area in here. The pdv work that you do is the area of this ellipse. So you find I squeezed it and I put in some work, and then it pushed back on me, but then it didn't push back on me as much as I pushed on it, so I don't get back all the work. So some of that energy went into heat or something. That's bulk viscosity. Any question about that? Okay. Right. So the thing I'm going to say now is bulk viscosity is at a maximum because that area of that ellipse is at a maximum when the fatter the ellipse is, the more area inside it, and that happens when you're at critical equilibration. So bulk viscosity, the amount of dissipated energy in one cycle, is at a maximum when you're at critical equilibration, when the flavor relaxation rate matches the frequency of the density oscillation. And you can actually calculate it. It's this function here with a rate over rate squared plus frequency squared, and it's got this sort of shape where the bulk viscosity, the amount of dissipation, is varying non-monotonically. It's got a maximum when the rate, I'm doing the rate along the bottom here, so this is the relaxation rate, and this is the bulk viscosity, and when the relaxation rate matches the applied frequency, you get maximum bulk viscosity. Now, I just want to say, because I'm getting close to the end, I just want to say a couple of words about what happens elsewhere. So remember, we talked about this before. Fast equilibration, this rate here, this gamma, goes to infinity. The material equilibrates very, very quickly. What do you see in this formula? If you take gamma, the rate, to infinity, the gamma squared on the bottom beats the gamma on the top, beats the omega, and so the bulk viscosity goes to zero. And that's this top end here where the rate is going very, very fast, and so the bulk viscosity gets small. And that's because it's always in equilibrium. That's your perfect spring. You squeeze it, and it does, you do work on it. You unsqueeze it, it does the same work on you, because at every point on the way in, it behaves the same at that point on the way out, because it's instantly equilibrated all the time. So there's no bulk viscosity in that case. So that's why this formula, makes sense and goes to zero. We can also look, remember we did slow equilibration. Slow equilibration is when this gamma relaxation rate goes to zero. Now you can see this bulk viscosity is also going to go to zero if the equilibration is very slow, because of this gamma on the top. But why is that sort of intuitively? Well, the system isn't even trying to equilibrate. Remember, the proton fraction is fixed. So again, it behaves the same on the way in as on the way out. The proton fraction is always whatever it is, 6%. So it's no different when it's 6% proton fraction, when you're halfway through squeezing or halfway through unsqueezing, it's the same material behaving the same way. There's no phase lag between different parts of the oscillation. So effectively, you've got another conserved quantity. And so again, there's no pressure density phase lag. So this is this bottom part of the curve here. At very slow equilibration, the bulk viscosity goes to zero. So you get maximum bulk viscosity, maximum loss of energy when you compress and uncompress. That maximum happens at this critical equilibration when the relaxation, when the relaxation rate and the frequency of the oscillation are about the same. Okay, then let me see. So that's this. So this is why I'll put them side by side now. So relaxation time, you've seen both these plots before. Relaxation time, remember, mostly depends on temperature and reaches critical equilibration, matching the 1 kilohertz. This is in this region here, and sure enough, the bulk viscosity has its maximum value here. And if you make the system hotter, then it equilibrates too fast, and there's no bulk viscosity. And if you make it cooler, it equilibrates very slowly, and there's no bulk viscosity. All right, so I think I will jump ahead now, skip that, because I've done enough to do. Yeah, okay. Let me just say a quick word about bulk viscosity in the neutrino trapped regime. This was all neutrino transparent, remember? Neutrino trapped, it's too fast. And so you can connect them up, and so you get these sort of plots where, as a function of temperature, you've got the neutrino transparent regime at low temperatures and the bulk viscosity gets big. And just when it's reaching its peak, you switch over to neutrino trapped because they get trapped at high temperature. So you can try and sort of put these two pictures together. But really, we need a proper neutrino transport solution in the middle, and that's hard. Okay, so summary, here we go. So the summary is that why do we love neutron star mergers? Well, there are many reasons, but the reason some of us love neutron star mergers is because they probe the dynamical response of high-density matter. It's not just that it's probing that phase diagram, because the phase diagram itself is all equilibrium stuff, right? Phases is all to do with, in equilibrium, what state are you in? But part of what's cool about neutron star mergers is not only do they probe an interesting range of densities and temperatures that aren't probed elsewhere. There's nowhere else in the universe where you get matter at twice nuclear density heated to 60 MeV temperatures, or 20, or 10, or even 5. Okay, neutron stars tend to be KeV temperatures. So they're interesting because of the range of densities and temperatures that they probe, but also because they're dramatic events. Stuff is happening. They're not just sitting there. They're probing the dynamical response of this matter on the millisecond time scale. And that gives you an opportunity to see what kind of relaxation processes are operating on that time scale. So in neutrino transparent matter, we saw you get critical equilibration in this temperature range. And that means you ought to include that relaxation in simulations if you have matter in that range that's neutrino transparent. And I didn't show you that calculation because, finite time. But if you work out the consequences of the bulk viscosity that you calculate from this, you find that it can damp density oscillations in tens of milliseconds. So if the bulk viscosity really is as big as the calculation of it in neutrino transparent matter would indicate, then in neutrino transparent matter at 5 MeV, the density oscillations can be damped quite quickly. And this matters because in a merger, things are happening on the 10, 20 millisecond scale. So if this bulk viscosity is damping those oscillations on that time scale, then it's going to affect the evolution of the merger. So we should care about it. Okay, so what would one do next? There's all sorts of things that you could do next. Firstly, as I've said, neutrino transparent, neutrino trapped are two extreme cases, so you really want to look at arbitrary neutrino distributions. I just talked about neutron, proton, electron matter. That's the most sort of ordinary, vanilla type of matter. But you can also look at hyperonic matter, which seems to have fast relaxation, or other forms of nuclear matter, pion condensed, nuclear pasta phases, if you know what those are, quark matter, which people here have been looking at very recently. You can look beyond bulk viscous damping at other manifestations of the equilibration of flavor. So it can cause heating, right? If you have bulk viscosity, it can cause heating. It can cause neutrino emission. Some of that energy that is lost from the oscillation may get emitted as neutrinos. So those may be consequences that aren't just damping of oscillations, they're something else. You also, as I was circling back to where I started in the beginning of the talk, flavor equilibration is only one of the things, one of the out of equilibrium phenomena that one could be interested in. You could also look at thermal conductivity and shear viscosity. And there's some estimates that indicate in the neutrino trapped form of matter, if there are fine scale gradients like 100 meters, which is not out of the question in a neutron star merger, then you might get some effects of neutrino-mediated thermal conductivity and shear viscosity. And finally, all this has been in the standard model, but I know, who doesn't love a little bit of physics beyond the standard model? Everybody loves that. So you can think about beyond the standard model physics and how it would affect a neutron star merger. So I'm going to show you a final slide from my student, Stephen Harris, with other people did this. So they did this now. This is axion emission, or it's really axion ALP, axion-like particle emission. So this is as a function of temperature for some piece of a region in a neutron star merger, and the axion coupling, this G thing. What's the time taken for a hot region to cool by radiating axions? And so this is the 1987A limit, and so the coupling is probably not bigger than that. So if you restrict yourself to down here, you find that if you have axions that are strongly coupled, but within the limit set by that observation, strongly coupled axions, then they're strongly coupled enough that they get radiated enough that if you have a very hot fluid element, like 60 or 80 or 100 MeV, they could cool it within tens of milliseconds. And again, that's an interesting time scale because that's the time scale on which the merger actually happens. So it is conceivable that even beyond the standard model physics could be brought in and could be relevant. So go back to that. And thank you.
Thank you, Mark, for the interesting colloquium. Questions?
So one of your messages that I take away is that it's critical to know if the neutrinos are trapped or not in the merger. I was wondering if you can establish that based on these numerical simulations by Ritzel and other people.
Yeah, so there's a whole industry of people doing what they call neutrino transport. And so it's complicated because, so if you take a region with a given density and a given temperature, it's got a spectrum of neutrinos with different energies, and neutrinos of different energies have different mean free paths. So you can't necessarily even say the neutrinos are trapped, right? You'll have high energy neutrinos with a short mean free path and low energy neutrinos with a long mean free path. And so you've got this, unfortunately, very complicated out of equilibrium situation. What the microscopic, so I'm focusing on the microscopic physics, right? So what a microscopic physicist can do is calculate things like these equilibration rates or absorption rates or something like that for an arbitrary neutrino distribution. And then you hand that table over to the merger people and they put that into whatever neutrino transport scheme they're using. So the hard part, I'm trying to outsource the hard part, right? Let them decide on neutrino transport and we'll provide the microscopic physics. But it is very hard, and I think at the end of the day, the reason for doing the neutrino transparent and the neutrino trap calculations is you can do them and they give you an indication. If it turned out that in both neutrino transparent and neutrino trapped, the relaxation was always super fast, everything was in equilibrium, there'd be no bulk viscosity, nothing to see here, no need to worry, okay? So the point of it is motive. Should we carry on down this road? And the answer is yes, but then the next step, unfortunately, is the rocky path.
Thank you.
Yes, thank you. So I wanted to ask that in a Neutron star merger, the amount of energy is such that when the merger takes place, the typical temperature is going to be 100 MeV, not few MeV. So don't you, I mean, to go down to this temperature where this effect is interesting, don't you have to wait a long time after the merger is over and it cools down to this temperature and then, you're going to be...
Okay, let's go back in our time machine, which is not very fast, but let's see if we can do it. Where did we start? Long, long ago. Here, okay. So this shows you what range of temperatures and densities is probed, right? That for every point, every fluid element is plotted on here. And this is one simulation with one equation of state. It's not definitive. But you see that 2 milliseconds after the merger, there is material in this 2 to 3 times saturation density range at temperatures in a single digit range, okay? Later on, that density range seems to be hotter. So you're kind of thinking of 10 milliseconds after the merger, and the middle density stuff is at 30, 40 MeV. But in this simulation, at least, in the early moments, remember this was when the oscillations were most violent in that first few milliseconds, there's hot material and there's not so hot material. It all depends where you are.
Right, but I mean, okay, so if you have the neutrinos from these hard regions, right, they're optically thick when you are at 100 MeV, so aren't they like, they should be mixing everywhere.
Right, okay, so probably these regions are experiencing a flux of neutrinos going through them. So that's all part of this neutrino transport difficult problem, which I'm not claiming to solve, right? I'm trying to understand what microscopic physics should be included.
Yeah.
So actually, I have a comment related to this image. That's good we are here. So for a neutron star, actually at the scale of the neutron star, everything is inhomogeneous. So if you want to kind of relate to what you are doing with these simulations and whatever we are going to see, somehow you have to introduce the inhomogeneities in your calculation. I understand that locally you may have everything homogeneous, so you can follow all these equations that do not care. But if you look at large scale of the neutron star, inhomogeneity should be quite important, as well as gravity, actually.
Absolutely. Again, though, this is all stuff that I can outsource to the neutron star merger simulators, because what a microscopic person needs to provide is a table as a function of density and temperature for a given fluid element, and maybe in the presence of a given neutrino distribution, what is the rate of relaxation of the proton fraction?
So you mean there is no interaction between different fluids at different distances?
That's a fluid mechanics problem for the merger simulation people to do, right? I mean, you have to sort of choose your area of, activity, right? So the argument here is just which physics should they include, right? And so the project here is, let's do some estimates and work out which phenomena they can ignore, right? If you measure something, you do some estimates and you say, this thing relaxes really quickly, and then they don't have to worry about it. They can just always assume every fluid element is in equilibrium with respect to that thing, whatever it is, right? But the whole point here is to do an estimate that shows there's some things that in some fluid elements will be out of equilibrium, and we be relaxing into equilibrium at the same rate as all the fluid dynamics is happening. And then you can't just ignore it, or pretend it's always in equilibrium, or pretend it's frozen out of equilibrium.
Okay,
right?
That's correct.
I mean, it's a sort of, so I'm thinking on a fluid element by fluid element.
So you're saying there is no interaction between long and short wavelength?
Well, no, there may be interaction. It's just that I'm trying to say what physics is relevant and needs to be included. I'm not saying what's going to be the result of including it in every fluid element in the simulation. I don't know. I'm doing the microscopic side, not the fluid dynamics side.
Hi. You mentioned that in order to get this relaxation time, you were considering the Orca processes.
Yes.
And I recall that in the evolution of a neutron star, the Orca processes were not very important because of Pauli blocking things, and the modified Orca processes were taking place. So I don't know whether in these conditions, at higher temperature, these modified Orca processes could also influence the calculation of the relaxation time.
Okay, so let me find a relevant slide for that. I have a paper that just appeared on the archive, which I claim is going to make modified Orca obsolete, but that's not this talk. So I will, for the now, tolerate the mention of modified Orca. Where are we now? Here we go. Okay, so this is those relaxation time contours, right? For two different equations of state. And what you notice here is this one has a sort of step down where all the relaxation times jog down about here. This one doesn't, okay? That jog is the direct Orca threshold. Okay, that's the thing you're talking about. So below this density, direct Orca processes are what drive the relaxation. Above the threshold, direct Orca processes drive the relaxation. Below the threshold, direct Orca is blocked and modified Orca processes take over. And that's why you have to cook it up to be hotter to get the same relaxation rate, because modified Orca is inherently slower. So when your density goes below the threshold, direct Orca shuts off. Now all you have is modified. Modified is slower, so you have to juice it up by making the temperature higher, and then modified Orca can reach your 1 kilohertz rate. So yes, this thing you're talking about is direct Orca or modified Orca, depending on the density. That's included in these rate calculations.
Okay.
Yeah.
I just wanted to come back to the question before the last about whether you need to take into consideration. So you seem to be, you want to solve the problem fluid element by fluid element, and then give that information to the outsource it.
Yeah. So
they put it together using hydrodynamics.
Yes.
But suppose that you're in a situation where neutrinos are important and the mean free path is 1 kilometer.
Mm-hmm.
then you can't decouple
Right.
the long
Well-
distance from the short distance.
Well,
right?
hang on. So, okay, so remember, so the title of the talk was Neutron Star Mergers as Material Science, right? So I'm studying the properties of the material, right? So properties like viscosity or neutrino opacity or stuff like that. So how you put it together in a big simulation is separate. So it just means the situation you're describing just means that the things that they are going to ask for are different. So they're going to ask for properties where there's a neutrino distribution that they will provide because it emerges from their simulation. They want to know in a fluid element with a given temperature and a given density and experiencing a given flux of neutrinos from the outside, what will happen, right? What rate will the neutrinos be absorbed? At what rate will neutrinos be created? Those are properties of the fluid element. But any fluid dynamics simulation is going to be based on taking properties of fluid elements and using them in the evolution.
But that's what I'm saying, that might not be applicable in the real
Well,
world.
it's applicable. It's just that you have to, they then become functions of the ambient neutrino distribution.
No, because to use hydrodynamics, you need to assume that you're looking at distances longer than the mean free path. And the
Sure.
mean free path is kilometers.
Yes.
Then hydrodynamics would not apply.
I agree. It's not hydrodynamics anymore. It's fluid dynamics of some kind, or it's dynamics. And let's call it whatever we want. I mean, this is what neutrino transport is, right?
Okay,
That's what they're doing. It's them.
It's their problem. I get the message.
It's their
yeah.
problem. You know, I'm trying to do the microscopic properties and work out which microscopic properties do they need as input to their simulation. I'm not trying to do their simulation for them. I'm just trying to be the provider of relevant microscopic properties. Which ones do they need? Which ones do they not need?
So we had already several questions. Unless there is something urgent, since it's around lunchtime, I think we can stop here. Okay. Mark will be here for tomorrow as well if you want to talk to him. So let's thank Mark again. And